want to talk to you both about our Plant Science Day. Some of you may know that we have an open house at the farm in Hamden every year, and it would be a great place, but we'll talk about that later. In any case, what I offered to talk about today is about climate change, and I imagine that everybody here is not skeptical about the reality, I hope, of climate change, the reality of global warming, and our role. All of us have a role in it, and we can minimize that role. None of us are going to probably abandon our cars entirely, but there are things we can do. But I want to talk about the science of climate change and how it impacts plant health. And that's where I have my field of research is in plant health. I'm a plant pathologist. We work on plant diseases. I specifically work on diseases of trees for the most part, although I have this project in the salt marsh. And salt marshes, by the way, are highly productive in carbon sequestration, more productive than forests, actually. So in any case, if you don't know it, you should know it now, that our mean atmosphere globally for the planet of atmospheric carbon dioxide, and this is just carbon dioxide, not methane, and not other molecules that we produce that go into the atmosphere and contribute to this cocktail of greenhouse gases. Carbon dioxide is by far the bulk of it, but there's also methane. There are also various NOxes, nitrous oxide, and other forms of that. So right now we are stably, but it's climbing, over 400 parts per million of carbon dioxide. And just to put that in perspective, the planet has not seen that number since more than 3 million years ago. So humans were not on this planet 3 million years ago. And what we also know from some very, very well collected data, the data are so convincing, it is remarkable to me that people want to bury their heads in the sand and deny this, is that before the industrial age, when humans, because we are innovators, that's our biology, started burning fossil fuels, the atmospheric carbon was about 270 or so parts per million. That was how much carbon was in the atmosphere. That number oscillated between 200 and 280 for about 500,000, half a million years. That's as far back as the data go. So humans evolved from our non-Homo sapiens ancestors when we were a different species of Homo, but when we were cohabiting with Homo neanderthalensis, around 200 to 280 parts per million. So 400 is not, we don't know that in terms of our evolutionary history, okay? And just like if you put on too many blankets in your house, you're gonna get hot. The planet is getting hot from too much of a blanket around it. It's as simple as that. So when people deny it, it's just this life would not have evolved on this planet if it were not for greenhouse gases. That's just a fact. We would be a cold, icy planet if we didn't have some greenhouse gases blanketing the planet so that plants could evolve, so photosynthetic organisms could evolve, and then later on, small animals, etc., could evolve. So if this rate of increase continues, atmospheric carbon will be at levels that are equivalent to actually even further back. So way before 500,000 years ago, millions and millions of years ago, the planet did have much, much higher levels of carbon in the atmosphere. The planet was hot, but there were no animals. There were no flowering plants. So what we have started doing and what we are continuing to do in terms of putting this blanket around the planet is going to create an atmosphere that is unlike anything that all of life on this planet that has been around and is continuing to evolve, but cannot possibly evolve at a rate that would keep up with what we are doing to the atmosphere and the consequence to our climate. Sorry to be, it's dark, but it's the reality. So globally, annually, the average surface air temperatures from 1906, so for like the last 100 years, if you go to 2016, we've increased the global average surface air temperature by 1 degree Celsius. That doesn't sound like a lot, but it actually is a lot, because that means that the oceans are also warming up. It also means that our climatic patterns are changing. So this is the warmest period in the history of modern civilization. That temperature that we are now experiencing, that's the warmest that any part of modern civilization has ever experienced. It's also worth noting that the last 4 years on this planet are the warmest, are the four warmest years on record. And that's another remarkable fact, I think, to grab, put your head around. And that is not, these are not anomalies, that is a trajectory, that is a path that we are moving towards. And we are seeing, as a result of that, weather extremes, including here. We are experiencing weather extremes for the forest fires out west and up north, are unknown to anybody's memory. Also, sea level rise. I live near the shore, and not far from New Haven and West Haven, and we are seeing sea level rise. We are experiencing sea level rise. And so it's also important for people to understand that climate change is not, the implications of climate change are not something that are something that we are leaving for future generations. It is something that we are also experiencing ourselves now. And if you think about the last few, and I'm going to go over a lot of weather data, and I hope it doesn't bore you too much, but it's really worth seeing the data. Just like I love those numbers. I'm a scientist, so I love data. And it's really worth seeing the weather data to realize that, and it is amazing to me also when I think about the last few winters that we've had, which have been wimpy winters, mild, with some weird, like the polar vortex phenomenon, which is also a phenomenon of global warming and climate change. That is the climate change that results from global warming. And also, when you talk to people, global warming and climate change are not synonymous with one another. Global warming is the result of the increase in greenhouse gases. Climate change is a consequence of that. So those are important distinctions to make. So the planet is warming and the climate is changing as a result, and that's important. But in any case, the sea has gone up in sea level about 7 to 8 inches since 1900, and 3 inches of that sea level rise has been since 1993. So not only are we seeing a trajectory, but it's not a straight line trajectory. The rate of change in our climate is also increasing. So the climate is changing and the rate of change is increasing. And also we're seeing an increase in daily tidal flooding down in Florida, where they have every time there's a high tide or a king tide now, the sea level is actually, have streets that flood every high tide, every day sometimes. And that's not from rain, that's just from sea level rise. What am I doing to advance? I said I know what I'm doing here.
Just click, yeah.
There we go. Okay, so climate change drought in the Northeast. So most of you know, and if you farm, you know, that rain events have become less frequent in the summer. Last summer we had, we'll look at the weather patterns, but last summer was a little bit of a relief, but the summers before that, I mean, as a tree biologist, I try to explain to people what happens as a result of the cumulative stressors year after year, decade, even over the course of a decade. We expect trees to last for decades. Trees don't just respond to an event in 1 year, they actually continue to respond to that over years. So the stressors that we impose on trees over the course of a few years sometimes will take years before they fully manifest. And that's something that we are learning more and more. Greater intensity rain events in the winter and spring. We've seen that this last winter, where we've had more rainy days than we've had snowy days. Some people like that. I find it creepy, myself. Heat waves more frequent and of greater intensity. And these cold spells also of greater intensity, the few that we have, and the swings in temperature. And if it's hard for us to adjust to, it's really hard for trees to adjust to, and also wildlife. Very, very hard on wildlife. Droughts are more frequent and of greater intensity, and the largest observed changes are actually, as far as North America is concerned, are in this northeastern part of the country, of the continent. So what this graph is showing you here, and I have my sources down here, and you can always contact me at the experiment station, and I can share some of this stuff with you. It's still available. The federal government, as much as they want to pretend like this stuff doesn't exist, you can still get the data, which really amazed me, because a lot of us, my friends at the EPA down in DC, we were all panicking, thinking that a lot of this stuff was going to get buried, or it's harder to find, but it's all available. But what this graph is showing you is, on the left, this is current science's confidence in the ability to attribute a particular phenomenon to climate change. So we have high confidence, we have low confidence. This is our understanding of the effect of climate change on this particular event. So each of these bubbles represents an event, and the further up you go on this arrow, not only do we understand more the relationship between climate change and the particular event, but we also have, this indicates high confidence in the association between climate change and that event. And so what I want you to notice is that these four phenomena, extreme cold, extreme heat, drought, and extreme rainfall, are all, there's high confidence in the ability to attribute those events to climate change, and there's very, very strong understanding that climate change is causing these phenomena. Does everybody understand that? Okay. I'm always worried that I'm going like too much, but if you get it, that's great. Okay, the U.S. Global Change Research Program, I don't know if anybody remembers that the NCA4, which is a U.S. government product, the fourth National Climate Assessment, was still released in spite of the administration that we are struggling under. And this climate science special report released projections, all of which just confirms the dire situation that we are in relating to climate change. If greenhouse gas emissions are stabilized, and they're not, but 2018, thanks to our booming economy, also resulted in record amounts of emissions from the United States. That's something worth pointing out. I'm not denying people the ability to make money, but I think it's really important to point out that it's not stabilized. But if they were stabilized, then we would still have committed the planet. It's sort of like once you give something a push, it's going to continue rolling. So this is the push. The greenhouse gas emissions are the push, and even if we were to stabilize our carbon emissions, there would still be warming because some of these things are set in motion. We call these positive feedback loops, or forcing is another term you'll sometimes hear. But this commits the planet to another 1.1 degree Fahrenheit. Sorry, I forgot to put the little degree sign there. Warming by the end of the century. That's not that far away, really. Don't forget, we are 1 year away from 2020, so we're 20% through the century. So projected increases in the number of days over 90 degrees. This is our historical climate in the eastern part of the United States. This is under a model that presumes lower emissions, which we could do that if we really put our minds to it, but we are not doing it. And this is under a model of higher emissions, which is what we're at right now. And I've highlighted...
Projected by the end of the century?
Yes. Yeah, I'm sorry, and I should have put that there, and thank you for pointing it out. But I've highlighted the Connecticut part, and of course it gets all pixelated and stuff, but you can see this is what we're historically familiar with right here. This was what would happen if we lowered our emissions. We'd still see warming, but if we continue on the path we're on now, this is what we're looking at. The number of days over 90 degrees per year, and we're looking into the 40 to 50 days. I mean, this is remarkable. It really is remarkable. And no, it doesn't mean that we can just start planting things that grow down south, because it doesn't mean that our winters are necessarily going to, it's not like you can just take the weather and just, blithely move it up into some other sort of paradigm. It doesn't work that way. So when it comes to plants and how drought, in plant physiology, it's an important thing to consider is how plants respond to drought. We can talk about annual precipitation, and it is interesting that last year we had a record amount of rainfall annually. But as far as plants are concerned, it doesn't really matter what the annual rainfall is. What really matters is what's the available water during the growing season. And so we don't really like to talk to, sorry, my graphics are not translating here that well, but in any case. So let's look at some weather patterns here. And this is all available, I should have, but the National Center for Information Services is a great place to get these data. And anybody contact me and I can get you the links to these, because it's really interesting. It's updated on a real regular basis. Very useful information. You can look at the Northeast, you can look at it by state, you can look at it for month by month, 3 month, 6 month periods, etc. This is 6 month period, roughly what I consider to be the growing season. This is how much, these are departures in precipitation from normal. And so for 2018, it wasn't that bad. I mean, this is not a 1 degree departure. We actually didn't have much in the way of departures. We had an excess of water in 2018 relative to normal. But we also, if we break this down into 3 month chunks, like January to March, you can see that we started out with, just sort of average rainfall in the early part of the year in 2018, but we're already a couple of degrees warmer than normal in January through March. And then if we're sort of going January, March to May, May to July. But you can see we're already, now we're looking at, on the scale here now, we're going into negative numbers in rainfall. So going into the growing season, we're already entering into, even in 2018, into a deficit of rainfall and into fairly normal temperatures. And then into the summer now. Now we're into early part of the late spring and early summer. We're now into rainfall deficit and starting to get warmer and warmer above normal. And then in the end of the growing season, we're okay with precipitation, but way warmer than what we historically are used to. And then the previous year, very similar, or actually a little bit different in the sense that 2017 was what we have gotten used to as a hot, dry summer. So we're going in this 6 month period, the whole growing season, we're at a rainfall deficit. 2016, again, very, look at those numbers down there. This is not 1 or 2 inches. This is a minus 10 inch deficit over the course of the growing season in 2016.
That was our severe drought year here, right?
2016 was, 2015 was, as you'll see, 2015 was, 2014 was, and I think I have 2013 was not quite as bad, but was also a drought year. And what I don't have here, because I tried to scale this down a little bit, is that our winters, especially the winter of 2012, was a really weird winter. We had warm weather in February, and the trees were just, so now we're looking at so many issues with trees. We have in the eastern part of the state what we're now calling oak apocalypse, because there's been this enormous dieback of oak trees from massive amounts of gypsy moth defoliation. But it's not just the gypsy moth defoliation, because rarely, if you're looking at a big tree disease problem, rarely if people say, what is the thing that's wrong with my tree, and I try to explain, it's not a thing. It is many things, and it is an accumulation, an accretion of stressors over time. And then what happens is that tree, just like a plant, can't respond. It doesn't have the resources to respond when something that normally it would maybe suffer from but not die from. But there are tens of thousands of oak trees in eastern Connecticut and Rhode Island that are just dead. And this is new, pretty new, that's this year. And no one quite knows who's going to pay to remove all of these trees. I mean, there's a great firewood resource there, but it's remarkable. So in any case, you can see that we have had year after year of growing season departures in precipitation. It doesn't matter, it's not like we're in California where you have snowpack and snow melt that can then provide water during the dry season. California is adapted, it's Mediterranean climate, it's adapted to not having rain during the summertime. We're not. And so this is dramatic. So when people talk about the new normal, because I'm typically contentious about things, I say no, it's not the new normal. There is no new normal because we are on a trajectory. So to say that, okay, now this is what we have now, we can say we're used to this, I would try and disabuse people of that way of thinking because it will continue to change. There is no new normal, or the new normal is different next year from this year and different the year after that, etc. So drought as a phenomenon, since we are probably going to have to live with drought as a reality, what is drought? It's a weather phenomenon. It's a long period of abnormally low rainfall, according to the dictionary. The National Weather Service defines it as a deficiency in precipitation over an extended period of time. And so that deficiency is relative to something, and that means relative to what we would consider normal. It results in a water shortage, and it of course has adverse impacts on vegetation, animals, and of course people. And these massive migrations that we are seeing globally, and I don't want to get too far off topic here, but the impacts globally of climate change and changes of weather patterns in these extended periods of drought in places where people rely on subsistence farming is having enormous impacts on people's lives, obviously. And just like with plants, people, when they are struggling to obtain even minimal amounts of nutrition, become more susceptible to disease. They are put into environments where other stressors accumulate, and they become much more susceptible to diseases. So these are really important consequences and things we should keep in mind. The National Weather Service also very conveniently breaks down drought into the different kinds of drought, and it's worth it as farmers and growers and anybody who should be thinking about the growing part of their environment. So we just talked about meteorological drought. That's just degree of dryness relative to some normal. But hydrological drought, especially in parts of the country where people depend on water supplies, is just where there's a depletion of a water supply. So, for example, in California, in the Sierra Nevada, where people depend on that snowpack, those tens and tens of feet that, in a good year, they get, slowly melts and then supplies their reservoirs, right? But if now with the snow line going up and up and up in the mountains, and more of that precipitation is now in the form of rain rather than snow, that rain is going to not be there to melt the following year. So even though they had more precipitation, it's not available. So they could be going into a hydrological drought as a result of that, even though their annual precipitation has not changed. And then there's agricultural drought, where there are soil water deficits. So deficits, groundwater levels go down, reservoir levels go down, and that impacts agriculture. So I talked about these three kinds of drought, and it's important to understand that these two kinds, this bracket should go down here, but these two kinds of drought are often experienced well beyond wherever meteorological drought occurs. And that, my example of California would be one way to demonstrate that. And then there's physiological drought, and that's not a National Weather Service definition. This is something that we talk about, which is where water conditions limit the ability of plants to grow. And it's often associated with a lack of water, but there are issues where there could be sometimes too much water and you can have drought-like conditions, and I'll explain that in a moment. It can be due to low temperatures where the groundwater is frozen, and if you have anybody here who grows mountain laurels or rhododendrons, and you see where there's a cold spell and the leaves kind of curl downward, those plants they're broadleaf evergreens. They not very aggressively, but they do photosynthesize over the course of the winter. But if all of a sudden their roots, you can't photosynthesize as a plant unless you have water moving through your plant, and we'll talk about that in a moment. But those leaves are curling because they don't have water available to them. There may be water in the ground, but if it's frozen, they are experiencing a drought. As far as the plant's concerned, it's a drought. High temperatures and high wind can also result in drought because the process of evapotranspiration through the stomates, as water is moving through the plant, cannot keep up with the evapotranspiration caused by the wind and the heat. Salinity, this is something on the shoreline that we are dealing with sea level rise and with storm surges. The deposition of salt changes the ability of, because salt is competing with the plant's ability to pull water up into the plant. It's called osmotic potential. I don't want to get into that too much, but salinity can create drought-like conditions. Excess water flooding can actually create drought-like conditions because it destroys the root's ability to take up water, and soil compaction, which is the result of flooding actually. So any concern about drought and the impact of drought on plants is really about water stress. And water stress is a much more relevant term to what we're talking about when we're talking about climate change and agriculture. And to understand water stress, you really have to understand water relations. So very briefly, why is vital water to plants and trees? Because 50% of a living plant is made up of water. And because the transport of metabolites and nutrients depend on water. Water is needed to deliver things from the soil up to the plant. You can't do it without water. Even desert-adapted plants do work with water. Also for evaporative cooling, and then of course for photosynthesis. Photosynthesis can't take place without water. Carbon dioxide, water, and light. Right? Carbon dioxide is one of the great things about plants, as Dina explained, is that when we have plants very well functioning, whether it's a salt marsh or a farm or a forest, those plants are using sunlight and water with the energy from the sun to take carbon out of the atmosphere and then build cellulose with it. And what happens with that cellulose, if it goes into the soil, you now actually, soils are a very, very important carbon sink. So carbon, water, and energy, carbon dioxide, water, and energy. And I mentioned the importance of water for plants. A lot of people are surprised to know this, but 90% of the water that a plant takes up, and this includes trees, is just released through the leaves. It's just this constant flow of water. It's one of the reasons why when you're around trees, it's cooler around trees, because they're actually, they're releasing water, and as a result of it, helping lower the temperature of the air. So that's the transpiration stream, but only 10% of the water that plants take up actually is going into photosynthesis. The rest is this transpiration process. So conditions that can give rise to water stress: excess water, a water deficit that we talked about a moment ago, the drought, and then of course frost drought, which I explained with relation to rhododendrons and mountain laurel. So excess water reduces the oxygen supply to roots, resulting in anaerobic decay and then root failure. And we see this all the time with trees where people overwater around the base of their trees, and then we start to see root failure and you start to see crown decline. I'm going to skip this slide. It's not that important. It's also kind of messed up. But in any case, drought stress, desiccation, and tissue damage results. So normally plants depend on producing phytochemicals. Any organism that can't move around, it's sessile, it's locked into the soil, has to have a really good arsenal if it's attacked, because it can't escape a predator, right? And a predator could be insects, a predator can be pathogens. So if you're going to be a well-developed or well-evolved plant, you're then going to have an arsenal of phytochemicals, which we take advantage of in what we eat. But these phytochemicals are largely the arsenals that plants develop in order to deal with pathogens, pests, stressors of all kinds. But if these plants are stressed, they're not going to be able to produce the phytochemicals that they need to produce, and so they're going to be much more susceptible to things like saprophytes or weak pathogens or insects. If that happens, then photosynthesis can often shut down, the metabolism of the plant shuts down. Coated is this thing about trees that I don't want to go into here, but it's going to be less likely to be able to outgrow or deal properly with the disease.
So what's going on with the oaks?
I'll talk about that later if you like. So once plants are established, one thing that you can do is eliminate or minimize competition for water. So anything that is competing with a plant for water is going, that's why we weed. It's one of the reasons why we weed, or some people weed. But weeds are going to compete for water, right? I mean, if you want to limit how much water you have to apply on a farm, you want to make sure that the water that you're applying is going to the things you want to grow. We mulch for that reason, because we're minimizing, we're also helping to prevent evaporation from the soil, but we're also keeping weeds down because weeds are competing for resources. It's just, with trees, over and over again, don't try to grow grass under a tree. I mean, that's just common sense to me, but, aerate the soil. And mulch. Mulch is really, really important. It slowly releases nutrients back into the soil, and it protects the soil from desiccation. For shrubs and trees, so if you're farming fruit trees, for example, this would apply, and that is that you want to restore moisture you want to keep moisture in the top 12 to 18 inches of soil. You can use watering bags, they're called tree gators sometimes, sprinklers, drip irrigation systems, and use a soil moisture meter. So in conclusion then, we're seeing increasing frequency of drought in eastern North America, with rain events that are far less frequent in the summer and fall and far more frequent in the winter and spring. We're seeing more frequent heat waves with greater intensity, and drought and heat are critical abiotic stressors to plants of all kinds, trees, any kind of plant. If you expose this salt marsh cordgrass that I work on, the pathogen that we are studying only causes disease and dieback of the salt marsh cordgrass only if the plants are stressed from either over inundation with salt water or not enough water. And it requires that stressor to then make this fungus, which normally cannot kill the plant, allows the fungus to kill the plant. And this applies to all kinds of plants. Drought and heat impact plants principally through water stress. Water is important for the reasons we talked about: photosynthesis, cooling, and transport. Drought can result in a buildup of salts and salts in the soils, and that's really important. So what happens is when you have drought and you have this buildup of salts in the soils, what does salt do? If you leave a salt shaker out in humid weather, what happens to it? It gets wet, right? So salt we call it hygroscopic. It likes water. So you have salt, and plants want to be able to pull water. They're basically, through transpiration, sucking water out of the soil. So, but now you've got salt pulling in the opposite direction. So it's like a tug of war. So the more salt you have in the soil, of all kinds, doesn't have to be table salt, any kind of salt. The more salt you have in the soil, the more pull you have against the plant's ability to pull water out. And that's why in a tree, when you start to see wilt or dieback in a tree or any kind of a plant, if you've got a lot of salt in that soil and you're putting water on it, you're not seeing any amelioration of that dieback, it's because of the salt in the soil. So that's really important. It lowers the soil water potential. Stomates close when transpiration stream shuts down, photosynthesis shuts down. It can cause irreversible damage to a plant's photosynthetic machinery, and sometimes to the point where the plant's not going to recover. You get the shutdown of photosynthesis, which means now, without photosynthesis taking place and the plant able to build up the molecules that it needs for defense, it's not producing those, and now you have increase in disease susceptibility. So drought, water is kind of like a key element to everything else that happens to a plant. All right, so that's my spiel, my sermon here. I can be reached at the experiment station. You just have to remember my last name. No one else has my last name at the experiment station. And I can provide you with links or any kind of information you like, especially